Series resistors. Let's look at this circuit. So this circuit, there's voltage source current I in this direction, terminal A and B, R1 and R2. Apparently R1 and R2 are in series connection. The voltage on R1 is V1 is marked positive sign, negative sign here, and voltage V2. With the current goes into this direction and voltage marked this way, the sign of convention is followed. Next, let's talk about the concept of equivalent circuits. This is a very important concept. We use it a lot. I mentioned this concept before in some of the videos. We're going to continue to talk about it because this is a confusing point that sometimes students make mistakes. The concept equivalent circuit. Let's look at this circuits here. What I care is terminal A and B, and there is a source here, voltage V. For the equivalent circuits, I do not care this connection, whatever the connection here, what way they are connected in series, in parallel, or in combination. At this portion, we can see here, all of these are resistors. Therefore, the equivalent of this portion must be a resistor, cannot be capacitor, cannot be inductor. Okay, that's point one. The second point is that we want equivalent circuits that we look at this terminal A and B here. We want these two circuits have the same terminal voltage and the same current that flow into the terminal. If these two conditions are satisfied, that these two circuits are equivalent in terms of terminal A and B. For example, if the value of the voltage here is 3 volts, if the value of the current here is 4 amp for this circuit, the value of V is 3 volts, the current is 4A, then in this circuit, it has to be the same. So V needs to be equals to 3 volt, and I needs to be equals to 4A. Only if these two conditions are satisfied, the same voltage on this terminal and the same current flow into the terminal or flow out of the terminal, depending on the direction that the current is defined. It doesn't matter which direction we define. Then these two circuits are equivalent. So next, let's look at what is R equivalent here. To figure that out, we need to look at both circuits. Let's look at the first circuits first. Let's apply KVL. So I'm going to start walking here. First elements, I'll write it here. So V1 plus, right? And now I keep walking, and then V2. And then just keep walking. And then now I encounter the negative sign first. That will be minus V equals to 0, because I'll come back to the same point here. Then what is V? V equals to V1 plus V2. Then let's figure out what is V1. Here we need to use Ohm's law. V1 equals to I multiplied by R1, and V2 equals to I multiplied by R2. Remember, R1 and R2 are in series connection, so they have the same current. We plug in, I'm going to write it here. So we plug in V1 and V2 using Ohm's law. Here we're going to have V equals to I R1 plus I R2. Okay, so this is from the first circuit. Let's look at the second, this equivalent circuit. So we need to figure out what's the value of this resistor here, Req. So how do we do that? We use KVL. Okay, so I start walking in this point. So you walk here. First encountered voltage is VEQ. Encountered positive sign first, so there is a positive sign here. And I keep walking here, and then minus V because I encountered negative sign first, so minus V. And from here, we can see V equals VEQ the current is flowing into this direction. So Ohm's law applies. That equals I multiplied by Req. These two circuits to be equivalent, V has to be the same, I needs to be the same. So let's mark this. This is the same V, this is the same V, that's the same I, that's the same I. So what is Req? We compare this two relationship. Req equals to R1 plus R2. These two resistors are in series connection. The equivalent resistor is sum them up. If I have many other more, I have more resistors are in series equivalent resistance. Req equals to summation of Rn, n equals 1 to big N. N is the number of the resistors in series connection. Next, let's talk about voltage division. It only applies to when the resistors in the elements are in series connection. If we have series connection, parallel connection, and they mix together, be really careful. So basically, voltage division is that I have this voltage here, VS1, that's a voltage here on this terminal. Let's say this is A, this is B, and then I have a whole bunch of resistors. They are all in series connection. For example, what about if I want to know the voltage on this R4? So namely VR4, what that equals to. This can be obtained directly using the formula of voltage division, but let's see how this is derived. Okay, let's use KVL. I start this point here. First, I encounter this voltage source plus sign first. So that will be V R1. And then I keep walking here. And VR2 plus same thing here. Just everything will be possible. VR3, VR4, and VR5 until come here. Okay, so VR3 plus VR4 plus VR5. When I walk to here, I encounter the negative sign first. That will be equals to minus VS1. And I keep walking here at this point again. Here. That equals to 0. Then we have VS1 equals to VR1 plus all of those VR5. So next, what's going on? We're going to apply Ohm's law. Ohm's law, VR1 equals to I multiplied by R1, VR2 equals to I multiplied by R2, etc. VR5 equals to I multiplied by R5. In all of this, because they are in series connection, they share the same current. So therefore we have the same current here. If we bring everything in, so just plug everything in here. I'm going to write it down. Plug this in, I plug this term in, plug this term in here, plug this term in here, and then we're going to have VS1 equals to I, R1 plus R2 plus R5. So I take out this quantity I here. What is I? I equals to, you do divisions here, that equals to here. To obtain the voltage on R1, this is our R1. VR1 is equals to Ohm's law. I multiplied by R1. I multiplied by R1. The current is this quantity here. This quantity here. So we're going to just put this quantity here. Everything in here as I highlighted here. Highlight this term here. It will be here. Everything will be here. So you can see R1 multiplied by this. I can organize this term a little bit. I take out the VS1 out. So here, take out VS1 out. It becomes R1 divided by R1 plus R2 and plus R5. The voltage on VR1 is equals the ratio of R1 and summation of the resistors and multiply by this voltage on the source, the voltage on the source Vs1 here. This is the voltage division is related with the ratio of this resistor and the sum of all the resistors in the loop which are in series connections. Special case is that we only have two resistors in the loop. Here only two resistors here, R1 and R2. So the voltage on R1 will be R1 divided by R1 plus R2 multiplied by V. V is this circuit here. Let's draw. This is a notation V. And then here is R1 and this is R2 and this is VR1 and this is VR2. Pay attention to the sign, the voltage sign here. This is positive, this positive, and this positive. You have to follow the sign of convention, otherwise this relationship does not hold.